Welcome to day 41 of our low-level design course. Today we will be discussing an extremely important topic in system design, error-resilient designs and defensive programming. In this session, we will explore how to design systems that can handle unexpected failures without affecting user experience. Whether you are working on small applications or large-scale enterprise systems, error resilience ensures that your systems are robust and capable of dealing with problems as they arise. Let's dive in. Today's session is structured around three key areas: error resilience, defensive programming, and practical strategies to create robust systems. First, we will define error resilience and why it's important to ensure that systems can function smoothly even in the face of errors. Next, we will discuss defensive programming, a mindset that helps us anticipate potential issues before they occur, and how adopting it can prevent many common software defects. Finally, we will look at some practical techniques for building resilient systems. This will help you design software that not only prevents errors but also can recover gracefully when things go wrong. Error resilience is the concept of designing your system so that it can continue to function correctly even when parts of it fall. Imagine you are using an online shopping platform and during checkout the payment gateway fails. A resilient system might allow the user to retry the payment, proceed with another payment method, or at least inform them of the failure in a friendly way. In essence, error resilience is about ensuring the system does not collapse entirely due to a single failure. It's about minimizing disruptions to the user and maintaining system stability. As we move forward, we will discuss different strategies for building resilience into your software. Now let's talk about defensive programming, a philosophy that focuses on writing code that anticipates and handles potential errors before they occur. In a defensive programming mindset, you are not just writing code to do what it's supposed to, you are rethinking about what could go wrong. For example, you might check if the input values are valid before processing them, or ensure that any external dependencies like APIs are functioning properly. Some common defensive techniques include input validation, where we verify that incoming data is correct before using it, and null checks to ensure that unexpected null values don't crash the system. By using defensive programming, you essentially defend your program from the many things that could go wrong, making your system more stable and secure. An essential part of defensive programming is exception handling. When errors occur, they should be caught, logged, and dealt with approximately rather than causing the system to crash. We organize we can organize errors using a exception hierarchy where different types of exceptions are grouped into categories. For example, database related errors might fall under a database exception class, while user input errors could fall under an input exception. Custom exceptions are useful because they provide more context about the specific problem that occurred, helping us to respond more intelligently. For example, you might have an exception that not only says errors but specifies insufficient fund in a banking system. Moreover, logging errors is crucial. It allows us to track the root cause of failures and resolve them. You will want your logs to be actionable, telling you not just that something failed, but why and where it happened. Designing for failure means planning for failure from the start. We can't predict every possible error, but we can make sure our systems are prepared for common issues. One common approach is to use fail-safe defaults. This means if a part of your system fails, the system automatically falls back to a safe state. For instance, if an online payment system fails, it might automatically offer the user an alternative payment method. Another important concept is graceful degradation. This ensures that even if one component of your system fails, the rest of the system continues working. For example, in an e-commerce site, the ability to browse products could continue even if the checkout service is temporarily down. Finally, retry mechanism allow your system to try an operation again after a failure. This can be especially useful when interacting with unreliable external services like APIs or databases by giving them a chance to recover without interrupting the user experience. One of the first steps in defensive programming is input validation. This ensures that the data your system receives is clean, correct, and safe. For example, consider a web form where users input their email address. We want to ensure that the email is in the correct format before processing it. Validating inputs like this prevents malicious input that could compromise your system, such as SQL injection or cross-site scripting. XSS attacks. In addition to validation, input sanitization is about cleaning input to ensure it's safe for use. Even if malicious data gets through, sanitization will transform it into a safe format. Together, these two practices form the bedrock of securing a system from unexpected or harmful data. Let's put what we have learned into practice. Your first task is to implement input validation for an email address. Your job is to create a function that checks whether the email entered by the user follows a valid form. This exercise will help you practice recognizing incorrect input patterns early, preventing issues from escalating into bigger problems. You will also get a feel of for designing simple validation logic, which is something you will use throughout our design work. Next, we will tackle exception handling in a banking system. Specifically, we will write a function that handles money transfers. As you implement this function, think about all the possible failures that might occur, like insufficient funds, invalid account numbers, or connectivity issues with the bank's database. You will need to catch these errors, log them properly, and inform the user without crashing the entire system. This exercise will give you valuable experience in making your code more fault tolerant and robust. For this next exercise, we will implement a retry mechanism for a web scraper. A web scraper often rely on external services to fetch data, and sometimes those servers may be temporarily unavailable. Your task is to implement a retry strategy that will attempt to connect to the server several times before giving up and reporting an error. This practice helps you handle transient errors in a way that prevents users from seeing failure messages unnecessarily. It's a common strategy used to enhance the reliability of external services. In this exercise, we will design a fail-safe module for a payment processing system. When a failure happens in the payment gateway, we need to ensure the system does not break down entirely. Instead, it should offer alternatives to the user, like retrying the payment or using a different payment method. Your job is to ensure that even if one payment method fails, the system continues to work smoothly without disrupting the user experience. Let's now look at some real-world examples of how companies handle error resilience. Take Netflix for example. They use a technique called chaos engineering to intentionally disrupt parts of their system in a controlled environment. This helps them discover weaknesses in their infrastructure and ensures that their systems can handle failures without affecting the user experience. Similarly, Amazon employs automatic failover and replication. If one server goes down, another takes its place, allowing the system to continue running without interruption. These are great examples of how large-scale systems design for failure. Your homework for today is to design a robust user registration system. Make sure to include input validation for all the fields such as the email address, password, and name. You should also handle errors gracefully, for example, checking for duplicate emails or invalid password formats. Additionally, implement fail-safe defaults such as allowing the user to retry registration if an error occurs and ensure the system does not crash if the database is temporarily unavailable. To summarize, today we have learned about defensive programming and error resilience and how they play a critical role in building robust systems. By using techniques like input validation, exception handling, and retry mechanisms, you can ensure your systems are able to withstand errors and continue functioning smoothly. The key takeaways is that a resilient system is not one that never fails, but one that can handle failures gracefully and recover quickly. With these practices, you will be able to design systems that are not only functional but also reliable and fault tolerant. Thank you for your attention.